This is lesson IA6, and the topic is complex numbers. As I finished the video for the previous lesson, I said, and this is our last lesson on radicals. Well, that was not completely accurate because the complex numbers come from a radical. I started out this lesson with a definition. The definition says the square root of -1 is I. This is a number. I know that it comes from our alphabet. Nevertheless, it is a number. Just like pi comes from the Greek alphabet, but it represents a number. So let's talk about what it means. The square root of 25 is 5 because 5 squared is 25. But when you work with negative radicands, say I had the square root of -4, well, it cannot be 2 because 2 squared is not -4. It cannot be -2 because -2 squared is not -4. There is no real number that squared will give you a negative. So mathematicians simply created a brand new number. The square root of -1 is now going to have a defined value of I because I squared equals -1. I hope you will take these two pieces and commit them to memory, that the square root of -1 is I, and that I squared is -1. Complex numbers are the next stage up in our number system from the real numbers. Remember that we had the rational numbers, which we abbreviated with Q, and the irrational numbers, which I like to abbreviate I with a little r. Together, they make up the real numbers. Well, there are numbers that are not real, and they are complex, and they are always in the form A plus, and A is some real number, plus some real number times the imaginary I. Now, the set of real numbers is a subset of the complex numbers. Complex numbers are real if and only if the B value is 0. So if you think about it, if B, right, this B, if it is 0, then the coefficient of I is 0, so I is gone, and you have just a real number. If instead the A is 0, then you have no real part, and at least many textbooks call these pure imaginary. But complex numbers usually have both parts. Pure imaginaries are a subset here, real numbers are a subset here. So you have been, without any definition earlier, you have been working with complex numbers, but it was the subset of real ones. So let's go on and take a look a little bit of this vocabulary. The set of all numbers in the form of A plus BI is called the set of, we already talked about this, it is complex numbers. If B is not 0, so remember we're talking about A plus BI. So if B is not 0, so B does exist, it's sitting there, then the number is also called imaginary. If B equals 0, then the number is also called a real number. So if b is there and there is an I, you can call it imaginary. If b is not there, because it's 0, then it would be called real. All the numbers that we will study will be complex numbers. They could be complex, they could be a subset of complex called real, they might be just called pure imaginary, but we are going to talk all about complex numbers. We're going to add them, subtract them, multiply them, and divide them. All right, number 2 says determine the conjugate of 6 minus 5i. Well, if you remember that I represents a radical, then the idea of having a conjugate, I hope, makes sense. Do you remember from the previous lesson that if you had 2 plus the square root of 3, that its conjugate was 2 minus the square root of 3, and so on. The conjugate of 6 minus 5i will be 6 plus 5i, and we will use conjugates similarly to how we did before. Now we're going to think about simplifying square roots that have negative radicands. If you have a negative under the radical, you can eliminate it by putting an I outside the radical. Then you can simplify the positive part, keeping the I. You would factor it into the square root of 25 times the square root of 3. So you would have 5i square root of 3. One more example might be, how would you simplify the square root of negative 20? Well, right away that is I times the square root of 20. But the square root of 20 is the square root of 4, the perfect square factor, times the square root of 5. And then this will be 2 times I times the square root of 5. And so we will do that periodically. The simplifying of the square root of 20 has not changed. The simplifying of the square root of negative 20, there is an I. Usually the I is written on the right side of any numerical coefficient. It is always written on the left side of the radical. All right, let's take a look at number 4. We're going to add two complex numbers, and our final answer needs to be in this format. To add complex numbers, it's very intuitive. We're going to add the real parts and add the imaginary parts. So if I add the real parts, the 7 and the 9, I get 16. If I add the imaginaries, I have negative 4i, positive 3i, which gives us negative invisible 1i. All you would write down is 16 minus I. And it is in the required format. Number 5. In this one, we're supposed to subtract, so I'm going to do what I've done in the past. I'm going to keep this parentheses, I'm going to keep the inside of these parentheses exactly as it is, 2 plus 2i, but I'm going to distribute the negative 1 to both terms in the second one. That makes minus 3 and plus 9i. Now I'm going to combine the real parts. Positive 2 and negative 3 gives me negative 1. I'm going to combine the imaginary parts. 2i and 9i gives us 11i. There is my complex answer. That is the difference of these two. All right, let's take a look at this next subtraction. I'm going to remove the parentheses by distributing the negative ones. No, there's not a 1 written there, but it is implied. So I have 7. Negative 1 times negative 5 is plus 5. Negative 1 times positive 5i is negative 5i. Negative 1 times negative 6 is positive 6. Negative 1 times negative I is positive invisible 1I. Now I'm going to combine all real parts and all imaginary parts. For the reals, I have 7 and 5, which is 12, and 6, that makes 18 for the real part. For the imaginaries, I have minus 5i plus 1i, which is minus 4i. So my answer is turning out to be always in complex form. Problem number 7. It says to multiply. Well, this is in the format of distributive property. So I have 5i times 4 gives me 20i. And I have 5i times negative 7i, which gives me negative 35i squared. Every time you see I squared, you're going to need to remember that I squared is equal to negative 1. And because it's equal to negative 1, and it's multiplied by this, it's always going to change this to a positive. So I have 20i plus 35, because remember, this is gone, replaced with negative 1, and it used to be negative 35, and so then when I multiplied it, it became positive 35. And typically, you would reverse the order of those terms. I'm using the commutative property. That's 35 plus 20i. In the next problem, we're going to multiply, and I'm going to be using FOIL. So the product of the first, it is negative 1 times 1, which gives me negative 1. The outer, I have negative 1 times I gives me negative I. The inner, I have 3i times 1, which is 3i. These are both imaginary. Combine them for 2i. Then I have the product of the last, which is 3i times I, which gives me 3i squared. And remember, that's going to change it to negative, so this is negative 3. Every time you have an I squared, the I squared is going to disappear, and it's going to change the sign of the factor that remains. I have two real numbers to combine for negative 4. I had negative 1, negative 3 for negative 4, plus the imaginary part, 2i. There's my answer. Let's look at number 9. Once again, I'm going to try FOIL. Product of the first, I have 5 times 2, which is 10. Outer, I have 5 times negative 3i, gives me negative 15i. Inner, I have negative 4i times 2, which gives me negative 8i. We go ahead and combine those to be negative 23i. The last, I have negative 4i times negative 3i, which is 12i squared. But let's do our change. I squared becomes negative 1. It causes this to change its sign to negative 1. This is negative 12. Combining the real 10 and the real negative 12 for negative 2, the imaginary combination was minus 23i. All right, let's take a look at number 10. We have some more multiplication, but maybe you notice something. 8 plus 6i, 8 minus 6i, these are conjugates. And hopefully you remember that when you have a sum of difference product, which is conjugates, let me make that go away, you need to multiply FOIL, but remember that the outers and inners are going to cancel out. So all you have to do is multiply the first. 8 times 8 is 64. Multiply the last. It will always start out being a negative. 6 times 6 is 36. I squared. But because it is an I squared term, and it always will be with these complex conjugates, that is negative 1. Negative 1 times negative 36 causes that to change signs. So you end up with 64 plus 36, which is 100. Something to note. The product of complex conjugates will always be a real number, and that's a very valuable fact to remember. Let's multiply some conjugates again. Number 11. If I multiply the first, and let me stop. Hopefully you observe that they're conjugates. Negative 1 plus I times negative 1 minus I. It is this sign and this sign being the only two things that are different in these two complex numbers. That's what makes them conjugates. Negative 1 times negative 1 is 1. Then the last, positive I times negative I gives us minus I squared. Well, there is an invisible coefficient of 1, so when that I squared disappears, it's going to be this negative 1 times this negative 1, which means plus 1. This is 1 plus 1, which is 2. Remember, the product of complex conjugates is always real. All right, suppose you're asked to square a complex number. Now, if you wanted to, you can use FOIL. I'm not going to, but you could use FOIL and multiply 7 plus 9i times 7 plus 9i. Those are not conjugates, they're the same. Instead, I'm going to use the squaring shortcut that we talked about in a previous lesson. Square the first. 7 times 7 is 49. Multiply these. That gives me 63i. But that represents both the inner and the outer. So I will double it. Multiply the coefficient by 2. That is 126i. And then square the last. 9 times 9 is 81. I times I is I squared. Need to pause. I squared changes this sign. So I have a 49 plus 126i minus 81. Combine the real parts. That will give me negative 32 plus 126i. All right, so we have added and subtracted by simply adding and subtracting the real parts, adding or subtracting the complex parts. We have multiplied by using our processes that we learned with polynomials, where we did distributive property, did FOIL, did the squaring, remembered sum and difference products, which involved conjugates. Now, when it says divide, remember that I is really the square root of negative 1. So I'm going to rationalize the denominator. I'm going to multiply by the number 1 in a fraction form, 8 plus I, 8 plus I. This numerator product is distributive property. 9 times 8 is 72. plus 9 times I is 9I over. Now this denominator will not only become real, it will become rational. So I will multiply the first for 64. I will multiply the last for negative I squared. But remember, there's an invisible one, negative 1 there. That I squared goes, changes the sign. This product is 64 plus 1, which means the denominator is 65. Now, on a piece of paper, I would not mind if you left the answer like this, but MyMathLab wants the result in standard form. Standard form is A plus BI. So to do that, the A part is this fraction, 72 over 65, plus the imaginary part is this fraction, 9 over 65 times I. When you write it in the A plus BI form, make sure that the A and the B have been reduced to lowest terms. If they need to be reduced, do so. All right, let's do another division. Remember, what is our process? We rationalize the denominator, multiplying by 1 minus I. 1 minus I. Because we have 1 minus I over itself, we really have the number 1, and it is the conjugate of the denominator. So for the numerator, we're going to have distributive property. 12 times 1, 12I times 1 is 12I. 12I times negative I is negative 12I squared. But I won't leave that. That I squared goes, changing the sign of that term. So I'm going to write the real part first. This is the 12 from here plus 12I. That's just common that the imaginary term goes at the end. All right, for the denominator, it's much easier. Well, it's at least equally easy. I multiply just the first. I get to ignore the outers and inners because these are conjugates. And I multiply the last. That's negative I squared. Remember, it's negative 1I squared. The I squared changes that to plus. That is a denominator of 2. Because it wants A plus BI form, that's A, 12 over 2 plus 12 over 2I. And as I mentioned in the last problem, you want to reduce that. 12 over 2 is 6 plus 6I. That is the quotient. Let's look at number 15. To perform the division, I really don't feel like I'm doing any division. I'm using the conjugate of the denominator, 3 plus 5I over 3 plus 5I. Going to distribute in the numerator. 2I times 3 is 6I. 2I times 5I is plus 10I squared. I squared causes that to become negative 10. Going to reverse the order and put the negative 10 first, and then plus 6I. That might seem odd, but that's very, very common. The denominator, I'm going to multiply first. 3 times 3 is 9. Multiply last. That's negative 25I squared. Change the I squared to negative 1. That causes that product to change. So add those for 34. This is all over 34. But remember, it wants standard form. So it's going to be, and I'll reduce in just 1 minute, it's going to be negative 10 over 34 plus 6 over 34i. That was the second fraction, that was b. Reduce each one of those. 2 is a common divisor, so that's going to be negative 5. 2 goes in there 17 times, plus 3 over 17i. All right, number 16 is going to be a little bit longer because the numerator has 2 terms also. Going to multiply by the conjugate of the denominator, 4 minus 3i, 4 minus 3i. Now, you might want me to write it out in a particular way. The numerator has to be done by FOIL, so I'm going to try to just write all of the terms of the FOIL. Product of the first, 3 times 4 is 12. Outer product, 3 times negative 3i is negative 9i. Inner product, 4i times 4i times 4 is 16i. Product of the last, positive 4i times negative 3i is negative 12i squared. We're going to get rid of the I squared, changing that to now plus 12. I'm going to go ahead and take another step on the numerator. Let's look at the real parts. 12, and now of 12, for 24 is the real part. The imaginary, negative 9i, positive 16i, is going to give me plus 7i. So that's my numerator. My denominator, these are conjugates. I don't have to worry about outers and inners. The product of the first is 16. The product of the last is minus 9i squared. The I squared goes, changing that to plus. That means the denominator is 25. My math lab would want this written as 24 over 25 plus 7 over 25i. And that's your final answer. You just want to take your time if you need to do FOIL as part of the problem. All right, we're going to talk about raising I to powers. Now, I don't know that if you became aware of this, but when you add two complex numbers, you get a complex number, a plus bi form. If you subtract, you get a complex number. If you multiply, you get a complex number. If you divide, you get a complex number. What would happen if you ended up with an I to the third or I to the fourth? Would it any longer be a complex number? Well, the answer is yes. So let's remind ourselves. The imaginary unit I is defined as I equals the square root of negative 1. Where I squared is equal to negative 1. I don't know if you remember from the very start of this video, I said, remember this and remember this. All right. Now, the next thing I have written here is remember. These are things that are going to be important, but I'm going to say them again and talk through it. If you have I and you raise it to the first power, you just get I. If you have I squared, we know by definition that's equal to negative 1. If you have I to the third power, well, I'm going to use the product rule with exponents and say, well, that could be I squared times I. Hopefully you understand that I just factored it. Why did I do that? because I know a value of I squared, which is -1, times I, that's -I. That's what I have written right there. If I have I to the fourth, I end up with, I could write it as I squared times I squared, which gives me -1 times -1, which is 1. I am very hopeful that you will commit these to memory, because let me show you what you could do, and then we're going to learn the shortcut. If I said, well, how about I to the fifth? You could say, well, I can factor it a lot of ways. I could call it I times I to the fourth, I to the second times I to the third. There are lots of ways you could do it, but I to the fourth is kind of my favorite because I to the fourth is 1. So I'm going to call this I to the fourth times I, which means it's 1 times I, which is I. I'm just looking at powers of I, and I'm hoping that we will see a pattern. Suppose I have I to the sixth. Well, I could factor it as long as the exponents add up to be 6. My preference is I to the fourth times I to the second, because 4 plus 2 is 6. Why did I choose that instead of 5 and 1 or 3 and 3? Because I to the fourth is equal to 1. So this is 1 times I squared, but I squared is -1, so this is 1 times -1. That's a times sign. So that's -1. If I did I to the seventh, I could say that's I to the fourth times I to the third. Well, I to the fourth is 1. I to the third, look over here or look up here, it's -I, so that's -I. I to the eighth is I to the fourth times I to the fourth, which gives me 1 times 1, which is 1. I want you to look, and I could continue with this for a long time. I, -1, -I, 1. I, -1, -I, 1. This is the pattern for all powers of I. And I do have it written over here. If you ever ran into I to the 0, that's the same thing as 1 as well. So I'm going to erase this. You know, you could go back and pause the video if you wanted to write any of that down. What I would encourage you to write down is this much. All right, now I to the 20th. All answers are going to either be I, -1, -I, or 1. Let me show you. You could say, oh, well, this is I to the fourth times I to the fourth, because I to the fourth is my favorite, times I to the fourth, keeps disappearing, times I to the fourth, I don't know why it's doing that, times I to the fourth. And it does not like my time signs. So my 4 times 4, my 4 plus 4 plus 4 plus 4 plus 4 all add up to be 20. My multiplication signs have disappeared again. I'm sorry, I don't know why. So this is 1 times 1 times 1 times... Okay, I'm just going to laugh at those multiplication signs disappearing. This is equal to 1. Another way you could do it, and this is a very time-consuming way, I don't recommend it, but it will work, count to 20 using this. You could say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So I to the 20th is equal to 1. Finally, a way that will work when you have larger powers of I. Take 20. divide it by 4. Why 4? You're taking all of the groups of I to the 4th out of it. That goes in there 5 times. It gives me 20 with a remainder of 0. It is the remainder that's important. I to the 20th is the same as I to the 0, which is 1. This is something you may have never experienced before, where the quotient is not what you're worried about. It is the remainder. Let's take a look at this next one. I to the 29th. Let's see. Take 29 and divide it by 4. That goes in there 6 times, which, I'm sorry, learn my division facts. 7 times, which is 28, with a remainder of 1. That means that if you were to count through this, going 1, 2, 3, 4, to get up to 29, you would go all the way through it 7 times, and then you would land on 1. So I to the 29th is the same as I to the 1st, which is just I. I to the 27th. Let's take 27, divide it by 4. It's going to only go in there 6 times, which is 24. Subtract for 3. The remainder is what you're looking for. I to the 27th is equal to I to the 3rd, which is negative I. So let's suppose, it's not one of your problems, but let's suppose that we had I to the 127th power. Well, I'm going to even change that. How about, go away. How about I to the, I'll just say 75th power. I don't want to count through that 1, 2, 3, 4 and keep wrapping around to see where I would land with 75. I want to take 4 and divide it into 75. That goes in there 1 time. 3, bring down the 5. That gives me 8. That's 32. Subtract for 3. I to the 75th power is equal to I to the 3rd power, which is negative I. You can do any power of I this way. Now, before I completely stop on this lesson, I want you to take a look at what the calculator can do. I accidentally opened it and then I accidentally closed it. So let's go back and give it a second to open. Your calculator can handle complex numbers. I think it's valuable for you to be able to do them on your own, but I'm not going to keep you from using the calculator. The I on the calculator, it's a little hard to see, but it is the blue function of the period. So, suppose I had, let me push this up. Let's suppose I had 4 plus 2i plus 7 minus 6i. And I grabbed the calculator. I can put in 4 plus 2, hit the second key, which is up here, it's the blue one, 2, then hit the period, I. Could have used parentheses, I left them off, it doesn't matter on addition, it would matter on subtraction. Plus, I should have done it as parentheses, 7, subtract, 6, second, period, close parentheses. Hit enter, and we get 11 minus 4i, and that's exactly what you would have gotten if you had just added the real parts and combined the imaginaries. What if you had 4 plus 2i minus 7 minus 6i. Parentheses, 4 plus 2 second of the period is I, close, minus, open, 7 minus 6, gotta get my I, which is second of the period, close. And I get negative 3 plus 8i. It really shortcut when you multiply. Let's multiply these two quantities. Open parentheses, 4 plus 2 second I. And then I will just immediately open parentheses, 7 minus 6 second I. Now I hesitated to even show you this because look how quick this is instead of FOIL. Done. And finally, you can use it for division. What if you had parentheses 4 plus 2 second period gives me I divided by, you have to use parentheses on these, 7 subtract 6 second period I. If you were doing it by hand, you would have to have the conjugate of the 7 minus 6i, or you can do this. Now here's a problem. My math lab doesn't like that. Let's see. I'm not sure. I'm going to hit math. Choosing number 1 says change to fraction. We'll see. There it is. 16 over 85 plus 38 over 85i. Oh my goodness, I probably should not have shared that with you, but it is so cool. Let's see if I did second I and I raised it to the 27th power. That should be negative I. Okay, that's a problem. So let's not use the calculator for the powers of I. I'm not sure about its programming. This is a very unusual answer. I would imagine it's probably correct, but it is a very unusual form. So I'm just going to say don't raise I to powers using the calculator. Instead, do it this way. We had I to the 27th power, and it was so easy to get this, and the calculator had a problem. So now I can officially say that we have concluded our lessons that involve radicals, which does include I, or the complex numbers, because I is the square root of negative 1. I hope that helps.